This video is for entertainment and educational purposes only. The information presented regarding ride-on toys, their assembly, operation and safety features does not constitute professional safety advice, mechanical instruction, or a guarantee of product performance. We are not liable for any injuries, damages, or losses resulting from the assembly or use of the toys featured. Viewers must strictly adhere to the manufacturer's official instructions, age recommendations, and safety warnings. Always supervise children during operation, and conduct your own due diligence when purchasing and assembling ride-on toys. Stop buying your kids useless plastic junk that breaks in a week. Seriously, look at the graveyard of forgotten toys in your garage right now. Millions of parents across the United States are burning billions of dollars annually on flimsy, low-voltage ride-on toys that barely survive the first trip down the driveway, much less a bumpy lawn. We are conditioned to accept that children's toys are disposable, that a battery dying after 20 minutes is just part of the experience, and that stripped gears are an inevitable rite of passage. But what if I told you that the industry has been quietly holding back on real performance? What if the standard 12-volt crawl is a choice, not a limitation? Today, we are breaking the silence on the top tier of ride-on vehicles. We are talking about engineering that rivals some adult recreational vehicles, battery life that outlasts your kid's attention span, and suspension systems that actually absorb impact. This is not about getting a cute car for a photo op. This is about understanding the mechanical leap that has happened in the high-end Power Wheels market and why the standard big-box store models are effectively obsolete. By the end of this video, you will see a machine that fundamentally changes the landscape of backyard playtime, and you will understand exactly why settling for the basic model is a mistake you cannot afford to make if you value durability and actual performance. You are watching this because you are tired of the disappointment. You are tired of spending your hard-earned money on a birthday present that results in a frustrated child pushing a dead vehicle back up a minor incline. You want a product that delivers on its visual promise. The problem we are solving today is the information gap in the premium ride-on market. Most parents rely on user reviews that focus purely on aesthetics rather than the critical components: the drivetrain, the battery chemistry, and the chassis construction. We are going to dismantle the marketing fluff and focus entirely on the specifications that dictate real-world capability. Consider the typical scenario. You purchase a standard 12-volt ride-on vehicle. The box claims a top speed of 5 miles per hour. What they do not disclose is that this speed is calculated on a perfectly flat, smooth surface with a lightweight child. Introduce grass, a slight gradient, or a heavier rider, and that performance degrades immediately. The motors strain, the plastic gears slip, and the thermal overload switch inevitably trips, leaving the child stranded. This is the reality of the mass-market toy. We are going straight to the other end of the spectrum. Today, we are looking at the potential outcomes of investing in a 24-volt, dual-motor system with variable speed control and actual rubber tires. We are going to examine the historical trends of ride-on toys to show you exactly how we arrived at this level of engineering. We will analyze case studies of standard plastic tires versus EVA foam and real pneumatic rubber to demonstrate the drastic difference in traction and ride quality. We are talking about disc brakes on a child's toy. We are talking about independent coilover suspension. This video will serve as your comprehensive masterclass in understanding what separates a genuine miniature vehicle from a hollow plastic shell. You will learn how to identify the weak points in standard designs and why specific upgrades are non-negotiable for longevity. You will understand the significance of a dedicated metal frame versus a unibody plastic chassis. We will cover the battery architecture, explaining why a sealed lead-acid battery might be sufficient for a mild neighborhood stroll, but why lithium-ion integration is becoming the standard for sustained, high-torque operation without the dreaded voltage sag. You will no longer be guessing when you walk down the toy aisle or browse online. You will have the mechanical literacy to evaluate these machines like a professional. You are about to witness the unboxing and technical breakdown of a vehicle that redefines the category, and once you see the internal components and the engineering applied here, you will never look at a standard Power Wheel the same way again. The days of accepting disposable, underpowered toys are over. Welcome to the new standard of backyard recreation. Right out of the delivery truck, the sheer physical presence of this box demands attention. We are in the year 2026, and the logistics of shipping oversized items have evolved, but when the freight carrier drops a 150-pound carton on your driveway, you immediately realize this is not a standard toy store purchase. Imagine if you are a parent like Dave, a homeowner in suburban Texas, who is used to carrying those lightweight, brightly colored cardboard boxes under one arm from the local big box retailer. This is entirely different. The sheer weight alone is the first undeniable indicator of the engineering hidden inside. Historical trends in the children's ride-on market dictate that weight correlates directly with structural integrity. Plastic is light, steel heavy-duty copper windings, and dense battery cells are heavy. As we approach this massive carton, you can see it is banded with industrial nylon straps and reinforced with heavy-duty corner protectors, signaling that the manufacturer understands the value of what is inside. Taking a utility knife to the reinforced packing tape reveals a packaging strategy that prioritizes extreme protection over cost-cutting. Instead of the typical brittle white styrofoam that shatters into a million static charged pieces all over your garage floor, this vehicle is encased in custom-molded, high-density polyethylene foam. This specific type of closed-cell foam is usually reserved for shipping delicate industrial equipment or high-end electronics. The fact that the manufacturer opted for this expensive packaging material immediately sets a precedent for the quality of the vehicle itself. It tells us that the components inside are heavy enough and valuable enough to require serious impact absorption during transit. As we peel back the top layer of this dense foam, the initial visual impact is striking. The familiar scent of cheap, off-gassing plastic is completely absent. Instead, there is the distinct industrial smell of fresh rubber and machined metal. The very first components we pull from the protective cavities are the tires, and this is where the divergence from traditional ride-on toys becomes aggressively apparent. Let us look at a case study of a standard consumer experience. Consider a family living in Arizona, where the harsh summer heat bakes the asphalt. Traditional Power Wheels use hollow, blow-molded plastic tires. Within weeks of use on hot pavement, those plastic tires wear smooth, lose all traction, and eventually crack straight down the middle. What we are unboxing right now completely eliminates that failure point. These are massive 14-inch pneumatic rubber tires with aggressive all-terrain tread patterns. They are practically identical to the tires you would find on an adult utility terrain vehicle, just scaled down. By pressing a thumb into the sidewall, you can feel the heavy ply rating. But the rubber is only half the story. If you look closely at the center hub of the wheel, you do not see a simple plastic hole meant to slide over a metal rod. You see dual-sealed steel ball bearings. The potential outcomes of utilizing sealed bearings are massive. Drastically reduced rolling resistance, meaning the motors do not have to work as hard, which directly translates to longer battery life and a significantly smoother ride. Lifting the main chassis out of the box requires actual effort. This is not a flimsy unibody shell that flexes under its own weight. Underneath the automotive-grade painted exterior body panels lies a fully realized powder-coated tubular steel frame. Imagine if a child accidentally drives off a curb or hits an unseen ditch in the backyard. With a traditional plastic unibody design, the chassis absorbs that impact directly, often resulting in stress fractures near the steering column or the rear axle mounts. By utilizing a dedicated steel perimeter frame, the structural load is distributed evenly across metal, isolating the cosmetic plastic body from the brutal mechanical stress of off-road driving. The powder coating is flawless, applied thickly to prevent rust and corrosion from wet grass or mud, ensuring the longevity of the frame for years to come. As we flip the chassis over to inspect the undercarriage, the sheer scale of the drivetrain becomes visible. Standard ride-on vehicles typically utilize small, 390 size motors that generate high RPMs but virtually zero torque. They whine loudly and struggle the moment they encounter resistance. What we are looking at underneath this ultimate model is a dual 775 series motor setup. These motors are physically 3 times larger than the industry standard. They feature massive internal cooling fans visible through the ventilation slots and thick, high-gauge copper windings designed to handle serious amperage without overheating. These motors are bolted into heavy-duty, reinforced nylon gearboxes. The gears inside are not the typical brittle plastic that strips the moment a child tries to accelerate up a hill. These are sintered steel gears, machined for precision and durability. The historical trends of toy degradation show that the gearbox is almost always the first major mechanical failure. By upgrading to a steel-geared transmission, this vehicle is engineered to handle massive torque loads without shearing teeth. Further inspection of the undercarriage reveals the suspension system, which is an absolute engineering marvel for a vehicle of this scale. We are not talking about a simple spring placed over an axle to mimic the look of suspension. We are looking at an independent, 4-wheel articulated suspension setup, utilizing authentic coilover shock absorbers. you can actually grip the shock and compress the heavy-gauge steel spring, feeling the hydraulic resistance dampening the rebound. This means that when the vehicle traverses uneven terrain, roots, or rocks, the wheels independently track the ground, maintaining contact and traction while the chassis remains relatively level. It fundamentally changes the dynamic of how the vehicle handles and how the child experiences the ride. But as we move toward the rear of the chassis to inspect the power delivery system, we encounter a heavy, sealed metal enclosure bolted directly to the frame, completely unlike the loose plastic battery trays we are accustomed to seeing. There are thick heavy-gauge wires shielded in braided loom exiting this box, leading toward the motors and the central control unit. The sheer size and structural security of this power box hint at an electrical architecture that is wildly advanced for this market. What exactly is housed inside this reinforced vault, and how does it manipulate the voltage to control those massive 775 motors without causing a catastrophic system failure? The answer to that lies in a technology typically reserved for modern electric road cars, and as we unbolt this enclosure, you are going to see exactly why the traditional battery is dead. We unbolt the 4 hex screws securing the thick steel lid, and the moment we lift it away, the reality of the 2026 engineering standard becomes undeniable. Sitting inside this weather-sealed compartment is not a pair of heavy, outdated sealed lead-acid bricks hastily wired together. Instead, staring back at us is a massive, custom-built 24-volt, 20-amp-hour lithium iron phosphate power bank, encased in a fire-retardant polycarbonate shell. Historical trends in the ride-on toy industry have relentlessly relied on sealed lead-acid technology. The industry chose lead-acid because it was cheap, not because it was effective. But the potential outcomes of using lead-acid are overwhelmingly negative for the consumer. Imagine if you are a parent like Marcus, a father of 2 in suburban Florida. Marcus spends 14 hours overnight charging a standard 12-volt ride-on car, only to watch his kids drive it for a miserable 15 minutes before the vehicle slows to an agonizing crawl. That phenomenon is known as voltage sag. As a lead-acid battery discharges, its voltage drops linearly and drastically. The moment the child hits the throttle, the massive power draw pulls the voltage down so far that the motors physically cannot maintain their revolutions per minute. The lithium iron phosphate chemistry we are looking at right now completely eradicates that flaw. These cells maintain a nearly flat discharge curve. This means whether the battery is at 100% capacity or 10% capacity, the motors are receiving a constant, high-voltage stream of power. The top speed remains the top speed until the moment the battery is safely depleted. But raw lithium power is volatile without proper regulation, and that is where the true brilliance of this electrical architecture shines. Bolted directly to the side of the battery casing is a sophisticated battery management system, commonly referred to as a BMS. In cheap, mass-market toys, the power runs straight from the battery to the pedal switch and directly into the motors, which is a recipe for thermal overload. This intelligent BMS acts as the central brain of the power supply. It actively monitors the temperature of the lithium cells, balances the voltage across each individual cell during charging to prevent degradation, and features an automatic low-voltage cutoff. Case studies of early lithium-ion adaptations in consumer electronics often highlighted catastrophic failures due to over-discharging. This BMS prevents that entirely. If the child attempts to drive the vehicle into a steep ditch and pins the throttle, causing the motors to pull extreme amperage, the BMS will instantly detect the abnormal current spike and safely cut the power, preventing the wiring from melting and the motors from incinerating. Following the thick, 10-gauge, silicone-jacketed copper wiring out of the battery box, we trace the power delivery route toward the front of the chassis. These are not the flimsy, 18-gauge wires found in department store toys that heat up and turn brittle over time. 10-gauge copper wire is designed to handle continuous high-amperage loads without generating excess electrical resistance. This thick wiring terminates at a heavy-duty electronic speed controller, or ESC, mounted high on the firewall away from potential moisture. The inclusion of a dedicated ESC is a monumental leap forward. Traditional power wheels use a simple mechanical on and off switch located under the gas pedal. When the child presses the pedal, the motors receive 100% of the power instantly. This causes a violent, whiplash-inducing jerk that wears out the plastic gears and scares younger drivers. The ESC changes the entire driving dynamic. It processes the input from a variable potentiometer located in the newly designed accelerator pedal. This means the power delivery is fully proportional. If the child presses the pedal down just a quarter of an inch, the ESC sends precisely 25% of the power to the motors, allowing for smooth, controlled creeping. As they press further, the power ramps up linearly. This soft start technology dramatically reduces the mechanical stress on the drivetrain. By eliminating the sudden shock of instant torque, the lifespan of the steel gears and the motor mounts is extended exponentially. Furthermore, the ESC features heavily finned aluminum heat sinks. As the electronic components process the high voltage, they naturally generate heat. The aluminum fins draw that heat away from the sensitive internal circuitry and dissipate it into the surrounding air, ensuring sustained performance even during continuous, heavy-load driving on a hot summer afternoon. Let us look deeper into the charging mechanism, because the frustration of standard toy maintenance is a massive pain point for consumers. With a traditional lead-acid setup, leaving the charger plugged in for too long boils the internal electrolytes and destroys the battery permanently. Parents are forced to set timers and constantly monitor the charging process. The potential outcomes of utilizing the smart charging ecosystem included with this ultimate model are completely hands-off maintenance. The included fan-cooled, rapid charger communicates directly with the onboard BMS. It delivers a high amperage bulk charge to quickly replenish the battery, and the moment it detects that the cells are perfectly balanced and full, it physically severs the charging current. You could leave this vehicle plugged into the wall in your garage for 6 months straight, and the battery would remain at a flawless, non-degraded state of charge. This level of electrical sophistication fundamentally transforms the vehicle from a disposable plaything into a legitimate, long-lasting machine. The upgrade from an estimated 300 charge cycles on a standard lead-acid battery to over 2,000 charge cycles on this lithium iron phosphate pack means this vehicle will likely outlast the child's interest in it. It can be passed down to younger siblings without needing a complete electrical overhaul. We have established that the chassis is virtually indestructible and the electrical system is over-engineered to industrial standards, but a machine with this much raw capability requires a command center that can actually harness it. As we shift our focus from the undercarriage to the interior cabin, we are going to power this system on for the very first time. You might expect a simple plastic steering wheel and a fake sticker representing a speedometer, but when I press the push-to-start ignition button on this dashboard, the entire console illuminates, revealing an interface that completely changes how a child interacts with their environment. The push-to-start ignition button on this dashboard is not a simple, spring-loaded piece of plastic designed to mimic reality. It features a tactile automotive-grade detent mechanism that requires deliberate pressure to engage. The moment that circuit closes, a deep, digitized engine roar pulses through the interior cabin. This is not a tinny, high-pitched piezo buzzer sound that you typically find in disposable toys. This system utilizes a dedicated, low-frequency audio driver mounted securely behind the firewall to generate a sound wave that you can actually feel vibrating through the steering column. Simultaneously, the entire center console sweeps to life. Historical trends in the toy industry show that manufacturers have ruthlessly cut costs in the cabin interior, relying almost exclusively on printed decals and cheap stickers to simulate gauges and dials. They assumed that the consumer would simply accept this facade. But the children of the year 2026 are digital natives, and the engineering team behind this vehicle understood that a sticker is no longer an acceptable substitute for functionality. What we are looking at in the center of the dashboard is a fully functional, weather-sealed liquid crystal display touchscreen. Let us break down exactly what this interface provides, and why it is a critical tool, rather than just a cosmetic upgrade. On the far left of the screen we have a real-time digital voltmeter. Why is this specific readout so absolutely critical? Imagine if you are a parent like Sarah, living in a sprawling master-planned neighborhood in suburban Ohio. You are 1.5 miles away from your house on a paved walking trail. With a traditional big box store ride-on, you are effectively playing a guessing game with the battery life. When that lead-acid battery inevitably dies without warning, you are forced to carry 50 pounds of dead weight and a frustrated child all the way back home. This digital display completely eliminates that agonizing scenario by giving you the exact voltage output down to the decimal point. You can monitor the power consumption in real time, allowing you to calculate your precise return radius based on the data, rather than relying on pure luck. Moving to the right side of the display, we find the integrated media control hub. We are looking at full Bluetooth 5.3 connectivity built directly into the vehicle. The potential outcomes of this integration mean seamless, high-fidelity pairing with any modern smartphone or digital audio player. A child can stream their own custom playlists, educational audio, or interactive stories directly through the vehicle. And the sound is not channeled through a single crackling speaker hidden under the seat. This vehicle features dual, water-resistant marine-grade speakers with durable polypropylene cones integrated directly into the upper roll bar framing. This positioning directs the audio downward toward the driver, cutting through the ambient noise of the motors and the outdoors, providing an immersive acoustic environment that rivals the sound systems in actual recreational golf carts. Let us shift our attention down to where the driver actually sits, because the ergonomics of a ride-on vehicle dictate how long the child will actually use it. If you examine the seating in a standard mass-market Power Wheel, you will find hard, unforgiving, blow-molded plastic with zero contouring. After 20 minutes of riding over uneven pavement or bumpy grass, the child experiences significant physical discomfort, leading them to abandon the toy entirely. Case studies analyzing extended play duration consistently point to physical comfort as the primary variable for long-term product engagement. To solve this, the Ultimate model features hand-stitched, perforated synthetic polyurethane leather seats. Beneath the weather-resistant surface is high-density memory foam that actively absorbs the micro-vibrations transmitted through the steel chassis. The perforations in the material allow for passive airflow, preventing the seating surface from becoming uncomfortably hot during the peak summer months. The safety restraint system is equally uncompromising. We are not dealing with a simple thin nylon lap belt that continuously slips off the shoulder and provides zero actual retention during a sudden stop. Because this vehicle utilizes heavy-duty 775 motors that deliver massive instant torque, a standard seatbelt is mechanically insufficient. This interior is equipped with a genuine, fully adjustable 5-point racing harness. The thick nylon webbing secures the child firmly across both shoulders, over the hips, and up through the pelvis, locking securely into a central quick-release buckle. This distributes any kinetic force evenly across the strongest points of the body, ensuring the driver remains planted in the foam seating regardless of the terrain angle or the acceleration curve. Moving up from the seating to the primary controls, the steering column instantly reveals another layer of mechanical sophistication. Traditional steering columns use a direct, unassisted mechanical linkage. It is usually just a simple metal rod connecting the plastic steering wheel directly to a rudimentary steering rack on the front axle. This outdated design translates every single bump, rock, and rut directly into the child's hands, causing rapid steering fatigue and exerting massive stress on the plastic steering components. This vehicle introduces an electronic power steering assist mechanism. When the child turns the wheel, a localized torque sensor detects the rotational force and engages a dedicated, metal-geared servo motor mounted directly on the rack. This servo physically assists in turning those heavy 14-inch rubber tires. The result is a steering feel that is incredibly light and responsive, allowing a smaller child to navigate tight turns and complex obstacles without needing the upper body strength required by an unassisted heavy-duty vehicle. Even the gear selector located on the center tunnel abandons the cheap, plastic sliding switches of the past. It is a machined aluminum shifter connected to heavy-duty microswitches. When the child pulls the lever from park to drive or pushes it forward into reverse, there is a loud, positive mechanical clunk. This tactile feedback ensures the driver knows exactly what gear is engaged before they press the accelerator pedal. A secondary switch panel controls a high-intensity discharge LED lighting array, including functional daytime running lights, brake-actuated taillights, and a blindingly bright LED light bar mounted to the upper cage. The potential outcomes for evening visibility are massive, allowing parents to actively track the vehicle from hundreds of yards away in near-complete darkness. But giving a small child access to variable throttle control, independent suspension, a heavy steel frame, and a 24-volt lithium power plant is a terrifying prospect for any parent. The sheer kinetic energy this machine can generate is enough to cause serious property damage or drive the vehicle into a dangerous situation in a matter of seconds. So, how do you hand over the keys without losing your mind? How do you prevent a highly motivated 4-year-old from driving straight into a neighborhood pond or out into a busy street? The answer is hidden in a small matte black transmitter that comes sealed in a separate anti-static bag. And the technology inside this little remote control override system is going to blow you away. As we slide this matte black transmitter out of its anti-static packaging, the first thing you notice is the weight. This is not the hollow, fragile piece of injection-molded plastic that usually accompanies mass-market toys. It features ergonomic, rubberized grips and a perfectly balanced chassis that feels exactly like a high-end hobbyist drone controller. Historical trends in the ride-on toy industry show that parental remotes were treated as an absolute afterthought. For decades, manufacturers relied on incredibly cheap 27 MHz radio frequency systems, Those old transmitters required massive telescopic metal antennas, and they were notoriously susceptible to interference. If your neighbor opened their garage door, or if another child down the street was playing with a remote control car, your child's vehicle could suddenly receive a rogue signal and accelerate uncontrollably. The potential outcomes of relying on that archaic technology were disastrous and frankly dangerous. The engineering team in 2026 has completely eradicated that vulnerability. What you are holding in your hand is a state-of-the-art 2.4 GHz frequency-hopping spread spectrum transmitter. Let us break down exactly what that means for your peace of mind. When you power on this remote and bind it to the vehicle, it does not just broadcast on a single static channel. Instead, the transmitter and the onboard receiver continuously jump between dozens of different frequencies thousands of times per second in perfect synchronization. If a specific frequency experiences localized interference from a household router or a cell tower, the system instantly bypasses it. This creates a digitally locked, impenetrable communication tether between you and the vehicle. The latency, which is the time it takes for your physical input on the remote to translate into a mechanical action on the vehicle, is virtually non-existent, clocking in at under 20 milliseconds. Imagine if you are a parent like Michael, living in a dense, heavily trafficked neighborhood in suburban Illinois. You are walking down the sidewalk while your 4-year-old navigates the driveway in this massive 24-volt machine. Suddenly, your child gets distracted by a dog across the street and aggressively turns the steering wheel, aiming the vehicle directly toward oncoming traffic. With a standard toy, you would be forced to sprint after them, desperately trying to grab the rear bumper before they reach the curb. With this advanced transmitter, you possess absolute, dictatorial control over the vehicle at a range of up to 300 feet. The moment Michael pulls back on the throttle trigger of the remote, the vehicle's onboard computer instantaneously overrides the child's input. The priority protocol is hard-coded into the electronic speed controller. The remote command always supersedes the pedal and steering wheel inside the cabin. But the most critical feature on this transmitter is a large, recessed red button located squarely in the center of the control pad. This is the emergency stop system, and its functionality is a masterclass in safety engineering. When you press this button, it does not simply cut the battery power and allow the heavy vehicle to coast forward under its own momentum. Coasting is incredibly dangerous when dealing with a machine that weighs over 100 pounds and is carrying a child. Instead, the emergency stop activates a rapid electronic braking sequence. The electronic speed controller instantly reverses the polarity of the massive 775 series motors for a fraction of a second, using the magnetic resistance of the copper windings to physically lock the drivetrain. This brings the vehicle to an aggressive, controlled halt within inches, completely immobilizing the chassis regardless of whether the vehicle is on flat pavement or a steep downward incline. Once the emergency stop is engaged, the child cannot restart the vehicle, press the gas pedal, or turn the steering wheel until you deliberately deactivate the lockout from the transmitter. Case studies involving early remote override systems often highlighted a glaring flaw. What happens if the parent drops the remote, or if the alkaline batteries inside the transmitter suddenly die while the vehicle is in motion? The engineers anticipated this exact scenario. The receiver inside the vehicle requires a constant, uninterrupted digital handshake from the remote to allow the child to drive. If that signal drops for more than 1.5 seconds due to dead batteries or venturing beyond the maximum range, the fail-safe protocol automatically triggers. The vehicle will smoothly decelerate to a complete stop and remain in a neutral lockout mode until the connection is re-established. You are never left in a situation where the vehicle can wander off independently. Beyond emergency intervention, this remote serves as a highly granular training tool. Young children do not naturally understand throttle modulation. Their instinct is to press the pedal completely to the floor immediately. To mitigate this, the remote features a 3-stage speed limiting toggle switch. In Stage 1, the electronic speed controller restricts the maximum voltage sent to the motors, capping the top speed at a brisk walk, which is roughly 2 miles per hour. This allows a novice driver to learn the mechanics of steering and spatial awareness without the anxiety of high-speed travel. As the child develops greater motor skills and confidence, you can remotely switch to Stage 2, unlocking 4 miles per hour. Finally, Stage 3 unleashes the full 24-volt potential, allowing the vehicle to reach its maximum speed of nearly 7 miles per hour. This phased approach transforms the vehicle from a potentially intimidating machine into a scalable learning platform that grows alongside the child's capabilities. Even the steering can be entirely managed from your palm. The directional wheel on the transmitter utilizes high-resolution potentiometers, meaning your steering input is perfectly proportional. If you turn the knob slightly to the left, the electronic power steering rack on the vehicle matches that exact angle. You can completely take over the driving duties, essentially turning this massive power wheel into a giant, high-end remote control car, while your youngest child simply sits in the cabin and enjoys the ride safely strapped into their 5-point harness. The level of control provided by this frequency-hopping transmitter completely redefines the parental experience. You are no longer an anxious bystander hoping for the best. You are an active, connected co-pilot with absolute authority over the mechanical functions of the vehicle. We have now thoroughly examined the indestructible steel chassis, the revolutionary lithium iron phosphate power plant, the advanced interior electronics, and the impenetrable safety override system. We understand exactly what makes this machine the absolute pinnacle of backyard engineering in the modern era. But knowing the components is only half the battle. Now we must transition from unboxing to the actual assembly phase, and this is where everything can go catastrophically wrong. Putting this vehicle together is not like snapping together a cheap plastic tricycle. It requires precision, specific torque settings, and an understanding of the mechanical forces at play. In fact, there is one highly specific, incredibly common mistake that 90% of parents make during step 4 of the manual when mating the rear axles to the gearboxes. If you make this single error, you will completely shred the sintered steel gears within the first hour of operation, transforming your expensive investment into a useless pile of metal. You need to see exactly how to align this drivetrain properly, and the visual demonstration of this process is absolutely critical. The solid steel rear axle of this machine is not a hollow lightweight tube like you find on inferior models. It is a dense, precisely machined piece of heavy-duty cold-rolled steel. If you look closely at the extreme ends of this axle, you will notice a series of raised longitudinal ridges. These are the splines. Now look inside the central hub of the heavy-duty nylon gearbox, housing that contains those massive 775 series motors. You will see a corresponding set of recessed grooves. The entire structural integrity of the power delivery system relies on these splines and grooves mating perfectly. Imagine if you are a parent like David, a father in suburban Michigan, assembling this vehicle late on a Friday night in the year 2026. David is exhausted, the lighting in the garage is poor, and he is rushing to finish the build before his kids wake up. He slides the gearbox onto the axle, pushes the heavy 14-inch rubber tire over the hub, and threads the primary lock nut onto the end of the shaft. He feels some resistance, but assuming it is just a tight fit, he grabs a wrench and forces the nut down, crushing the assembly together. This is the exact moment the catastrophic error occurs. Because David did not take the time to slowly rotate the wheel and feel for the physical, tactile drop of the splines locking directly into the gearbox grooves, he effectively clamped the entire system down out of alignment. The potential outcomes of this rushed assembly are financially devastating. When you force that lock nut down on a misaligned spline, you are physically warping the reinforced nylon housing of the gearbox. This lateral pressure pushes the internal sintered steel gears out of their perfect parallel alignment. The very next morning, when the child climbs into the driver's seat and presses the accelerator, the lithium iron phosphate battery dumps massive amperage into those upgraded motors. The motors generate instant, immense torque, but because the gears are pinched and bound together by the warped housing, they cannot spin freely. The mechanical stress has nowhere to go but directly into the teeth of the gears. Within 60 minutes of driving on the grass, the binding friction will cause those steel teeth to overheat, grind against each other, and completely shear off, leaving the vehicle entirely immobile with a destroyed transmission. Historical trends regarding consumer complaints in the high-end ride-on market show that nearly all early drivetrain failures are a direct result of this specific user-end assembly error. To avoid this, we must throw away the cheap, stamped metal wrench included in the blister pack. That tool is a liability. You need a proper half-inch drive socket set and a calibrated torque wrench. When we slide the gearbox onto the axle, we do not apply any pressure. We gently rotate the entire motor assembly back and forth by hand. You have to actively listen and feel for the heavy metallic click as the splines successfully engage the receiver hub. Once engaged, the gearbox should sit completely flush against the steel chassis mounting plate with absolutely zero daylight visible between the components. Before we mount the rubber tire, we are going to take an additional preventative measure that separates a professional assembly from a standard amateur build. We are applying a liberal coat of marine-grade, high-temperature synthetic grease directly onto the exposed splines. Even though the internal gearbox is pre-lubricated from the factory, coating the external mating surfaces prevents moisture intrusion, completely eliminating the risk of rust welding the wheel to the axle over years of outdoor use. Now we slide the wheel onto the hub, followed by the heavy steel washer, and finally the nylon insert lock nut. Here is where the torque wrench becomes strictly necessary. You cannot simply tighten this nut as hard as humanly possible. The wheels utilize dual-sealed steel ball bearings. If you over-tighten the central nut, you will apply severe lateral compression to the bearing races, crushing the tiny steel balls inside and completely destroying the rolling efficiency of the tire. The proper technique is to tighten the nut just until the wheel stops wobbling laterally on the axle, and then back the nut off precisely 1/8 of a turn. You should be able to spin the heavy rubber tire with a single finger, and it should continue to rotate freely for several seconds with zero resistance. With the rear drivetrain perfectly aligned and secured, we move to the independent coilover suspension system. Standard ride-on toys often use cheap friction caps to hold their simulated suspension springs in place. These caps inevitably pop off the moment the vehicle hits a curb, causing the entire suspension arm to collapse. This ultimate model utilizes solid steel mounting bolts secured by heavy-duty nylock nuts. A nylock nut contains a tough nylon collar integrated into the threading. When you torque it down, the steel threads bite into the nylon, creating an incredibly tight friction lock that cannot be vibrated loose. Considering the intense vibrations generated by driving a 150-pound machine over rough terrain, these specialized fasteners are absolutely essential for maintaining the structural geometry of the chassis. We line up the steel shock absorbers with the welded brackets on the rear subframe, drive the bolts through the solid metal bushings, and secure them tightly. You can immediately press down on the rear bumper and watch the dampeners compress and rebound smoothly, ready to absorb the kinetic energy of the backyard. Transitioning to the front of the vehicle, the steering assembly requires an equal level of exact precision, specifically because we are dealing with an electronic power steering rack. Case studies of early power steering implementation in miniature vehicles revealed a major calibration flaw. If the steering linkages are attached while the internal servo motor is not perfectly centered, the vehicle will have a tight turning radius in one direction and virtually no turning capability in the other. Worse, the onboard computer will constantly fight to find the true center, keeping the servo motor engaged and draining the battery rapidly even when the vehicle is sitting still. Therefore, before we attach the heavy steel tie rods to the front steering knuckles, we must power on the dashboard, allow the computer to boot up, and let the electronic steering rack perform its self-calibration sweep. You will physically see the steering mechanism swing all the way to the left, all the way to the right, and then snap rigidly to dead center. Only then can we safely bolt the linkages together. We now have a rolling chassis. The 14-inch rubber tires are perfectly seated. The transmission is safely aligned without binding. The coilover suspension is dialed in, and the electronic power steering is mechanically calibrated. The physical skeleton of the machine is flawless. But none of this mechanical perfection matters if the electrical nervous system is compromised during the final integration. There is a hidden parasitic drain issue lurking within the primary wiring harness assembly of these advanced 24-volt models. It is a trap that can permanently kill the sophisticated lithium iron phosphate battery overnight if you miss one tiny, easily overlooked connection hidden deep behind the dashboard panel. We have to dive into the main control board to make sure your investment does not become a static display piece by tomorrow morning. As we pull away the temporary protective plastic shielding from the rear of the dashboard console, we are greeted by a chaotic nest of multicolored wires terminating in various white plastic Molex connectors. To the untrained eye, this looks incredibly intimidating, resembling the internal wiring of a high-end custom computer rather than a children's toy. In the past, connecting a steering wheel involved pushing one metal spade connector into a plastic slot. Today, we are dealing with multiplex digital signals, pulse width modulation data lines, and constant power draws. The specific issue we are hunting for involves the standby power circuit. Modern ride-on vehicles from the year 2026 utilize smart technology, meaning that even when the vehicle appears to be turned off, certain systems remain in a state of passive alertness. The Bluetooth module is waiting for a pairing signal, the remote control receiver is listening for a digital handshake, and the liquid crystal display is maintaining its internal memory. This state of passive alertness requires electricity, creating what engineers refer to as a parasitic drain on the power supply. Imagine if you are a parent like Christopher, living in a quiet neighborhood in suburban Washington. Christopher spends 3 hours meticulously assembling this ultimate power wheel on a Saturday afternoon. He connects the main battery terminal, hears the system beep, and assumes everything is perfect. The kids drive it all afternoon, park it in the garage, and go to sleep. When they wake up on Sunday morning ready for another adventure, the vehicle is completely dead. Christopher plugs in the rapid charger, but the charger flashes a red error light. What happened? Because Christopher failed to properly configure the sleep state jumper wire behind the dashboard, the vehicle never actually shut down. The parasitic drain silently pulled power from the 24-volt lithium iron phosphate battery all night long. Because the main power relay was bypassed by this error, the battery management system was tricked into ignoring its own low-voltage cutoff protocol. The battery was drained below its minimum safe voltage threshold, effectively destroying the internal cell chemistry and turning a highly expensive power plant into a useless paperweight overnight. Historical trends in the transition from analog toys to digital ride-on machines indicate that this single oversight accounts for nearly 70% of all early battery replacement claims. To prevent this from happening to your investment, we need to locate a very specific thin-gauge yellow wire bundled near the primary ignition switch harness. This is the logic bypass circuit. Out of the box, for shipping purposes, manufacturers often leave this circuit open to ensure the battery cannot be accidentally drained while sitting in a warehouse container for months. You will notice a small black plastic jumper clip tethered to the main wire loom. We must physically insert this jumper into the 2-pin receiver port, located on the back of the ignition module. This simple action bridges the circuit, routing all standby power directly through the master battery management system. Now, when the push-to-start button is held down for 3 seconds to power off the vehicle, the computer actively severs the power connection to the Bluetooth radio, the electronic speed controller, and the lighting array, reducing the parasitic drain to an absolute zero state. The lithium cells are now protected, and the vehicle can safely sit in your garage for the entire winter season without losing its charge. With the logic bypass circuit correctly configured, we can address the primary umbilical cord connecting the dashboard to the main chassis motherboard. We are not dealing with thick analog copper cables here. We are looking at a flat 24-pin data ribbon cable. This cable is incredibly fragile. If you try to force the male end into the receiver port at an incorrect angle, you will instantly bend or snap the microscopic gold-plated pins inside, causing complete communication failure between the steering wheel and the steering servo, or disabling the throttle completely. The correct method requires aligning the small plastic locking tab on the connector with the corresponding notch on the port. You must apply gentle, perfectly even pressure across the entire width of the connector until you feel a definitive soft click. Once seated, there is a secondary sliding lock mechanism that must be pushed forward to securely clamp the ribbon cable in place, ensuring that the intense vibrations from off-road driving will not slowly back the connector out of its socket over time. Now we must manage the physical routing of these wires. A massive case study regarding interior cabin safety in premium ride-on toys revealed a shocking hazard involving loose wire looms. If the wiring harness behind the dashboard is not tightly secured, the constant movement of the vehicle can cause the wires to droop downward into the footwell. The steering column, which is a rapidly rotating solid steel rod connected to the electronic power steering rack, passes directly through this area. If a loose wire gets caught around the steering column, it will instantly wrap tightly around the metal shaft as the child turns the wheel. The sheer rotational force of the steering servo will rip the wires completely out of the motherboard, sparking a potential short circuit and instantly disabling the steering while the vehicle is in motion. We absolutely cannot allow this to happen. Using heavy-duty automotive-grade zip ties, we bundle the entire wiring harness tightly together and anchor it to the pre-molded plastic mounting points located high up underneath the cowl, pulling it completely taut and entirely out of the rotational path of the steering column. We then finalize the dashboard installation by snapping the heavy plastic console panel into the main upper body shell. It is critical to press firmly around the entire perimeter of the display screen to ensure the weatherproof rubber gasket seats properly against the plastic. We are building a machine meant to survive muddy puddles and sudden rain showers, and any gap in this seal will allow moisture to directly attack the liquid crystal display and the sensitive microprocessors we just finished wiring. We power the system on one more time to verify that the digital voltmeter illuminates, the startup sound sequence triggers, and the steering wheel communicates flawlessly with the front rack. The electronic nervous system is now fully integrated, protected, and completely safe from parasitic drain and mechanical interference. The core of the vehicle is alive, but a bare chassis and a dashboard do not make a car. It is finally time to lower the massive, beautifully painted exterior body shell onto the steel frame. This process seems straightforward, but hidden within the rear roll cage assembly are the primary structural anchors for the 5-point safety harness. If you secure the body shell without properly routing these heavy nylon straps through the reinforced steel subframe brackets first, you are completely compromising the entire safety restraint system, rendering those heavy-duty seatbelts entirely useless in a collision. You need to see exactly how these impact anchors interlock before you drive a single screw into the exterior body panels. You need to see exactly how these impact anchors interlock before you drive a single screw into the exterior body panels. If you examine the lower tubular subframe beneath the seating area, you will notice 4 heavy-duty, forged steel D-rings welded directly to the main chassis rails. This is the foundation of the 5-point safety harness system. In standard mass-market ride-on toys, the seatbelts are nothing more than thin ribbons screwed directly into the thin plastic backrest with a single cheap self-tapping screw. For parents who are absolute beginners in mechanical assembly, let us provide a brief educational concept overview of impact distribution to understand why that cheap design is so dangerous. When a vehicle is in motion, both the machine and the passenger build up kinetic energy. If the vehicle suddenly stops by hitting a solid object, the passenger continues moving forward at the previous speed. If the seatbelt is only anchored to flexible, brittle plastic, the concentrated kinetic force of the child shifting forward will instantly rip the screw straight out of the plastic housing. The seatbelt completely fails precisely when it is needed the most. By contrast, the Ultimate model utilizes a motorsport-inspired anchoring system. Before we lower the beautifully painted exterior shell, we must take the heavy nylon webbing straps of the harness and route them upward from the steel D-rings, passing them carefully through the precision-cut vertical slots molded into the firewall and the rear bulkhead of the plastic body tub. You have to ensure there are no twists in the webbing, as a twisted strap dramatically reduces its tensile strength and creates uncomfortable pressure points on the driver. We weave these straps through the slots, maintaining tension, and then slowly lower the massive one-piece impact-resistant ABS plastic body shell over the steel skeleton. You have to watch carefully as the shell descends, ensuring that the main wiring harness we meticulously secured earlier is not being pinched between the rigid plastic and the metal frame rails. A pinched wire here could slowly chafe through its silicone jacket over time, leading to a catastrophic short circuit. Imagine if you are a parent like Jessica, a mother living in a cul-de-sac in suburban Pennsylvania in the year 2026. Jessica has a 6-year-old son who loves to drive his 24-volt vehicle at maximum speed across their sprawling, uneven backyard. One afternoon, he misjudges a turn and clips a hidden tree stump at roughly 6 miles per hour. The vehicle comes to a violent, immediate halt. Because Jessica properly routed the 5-point harness directly to the welded steel chassis anchors rather than relying on the plastic body shell, the immense forward kinetic energy generated by her son is transferred safely through the thick nylon webbing and absorbed entirely by the heavy steel frame. The child remains securely pinned to the high-density memory foam seat, completely unharmed and barely jostled. The potential outcomes of that exact scenario in a cheaply constructed, unibody plastic toy usually involve the child striking the steering wheel or being thrown completely over the dashboard. Historical trends regarding consumer product safety reports for children's ride-on toys consistently highlight seatbelt failure as a primary cause of injury. The engineering team behind this machine eliminated that variable by separating the cosmetic exterior from the structural safety components. Once the body shell is perfectly seated over the frame, and the seatbelt straps are visibly pulled through their correct routing channels, we can finally begin the process of mating the shell to the chassis. But again, we are not using simple wood screws. We are utilizing M6 stainless steel machine bolts paired with oversized fender washers and nylon insert lock nuts. A fender washer is critical here. Its large surface area distributes the clamping force of the bolt over a wide section of the plastic, preventing the bolt head from cracking or pulling through the shell when the vehicle flexes over uneven terrain. You must tighten these bolts in a specific star pattern, alternating from the front left to the rear right, ensuring the body settles evenly onto the rubber isolation mounts located on the frame rails. These rubber mounts serve to dampen the extreme chassis vibrations, preventing them from transferring into the plastic body and creating an obnoxious rattling sound as the vehicle drives. This aligns perfectly with the stringent manufacturing standards expected within the United States market today. With the main tub secured, we turn our attention to the upper roll cage structure. Many consumers mistakenly believe that the roll bars on children's toys are purely cosmetic aesthetic additions, designed to make the vehicle look rugged. On standard models, this is absolutely true. They are usually hollow, brittle plastic tubes that will shatter upon impact. However, The upper structure of this ultimate model is an actual functional safety device constructed from powder-coated tubular steel, encased in high-density polyethylene foam. Case studies of off-road driving dynamics in scaled-down vehicles show that an increased ride height, combined with aggressive rubber tires, naturally raises the center of gravity. If a child attempts to navigate a steep side hill gradient and the vehicle tips over, the upper structure must be capable of supporting the entire 150-pound weight of the machine to protect the occupant's cabin. Assembling this cage requires sliding the heavy steel upper tubes into the reinforced receiver brackets mounted behind the seats. But before you slide them together, you must locate the secondary wiring harnesses hidden inside the tubes. These specific wires provide power to the marine-grade speakers and the high-intensity overhead LED light bar we discussed earlier. You have to connect the weatherproof bullet connectors tightly, applying a small amount of dielectric grease to the terminals to completely seal out ambient moisture. Once the wires are connected, you carefully tuck the slack back into the hollow tube and push the cage downward until the locking pins click aggressively into place. You then secure the primary junction points with heavy-duty cross bolts, locking the entire upper canopy into a rigid, unified structure. The massive LED light bar is then bolted to the front horizontal crossmember, and you can route its dedicated power cable down the driver's side pillar, plugging it directly into the auxiliary port on the main dashboard harness. The final exterior components include snapping the shatterproof polycarbonate windshield into the front cowl. This material is specifically engineered to bend and flex upon impact, rather than shattering into dangerous, sharp shards. Next, we attach the side view mirrors. These are not rigidly fixed to the doors. They feature a spring-loaded breakaway mechanism. If the child accidentally sideswipes the side of the garage or grazes a fence post, the mirror assembly will forcefully fold backward against the door panel, absorbing the blow without snapping off, and can be easily snapped back into its original position. The physical assembly of the vehicle is now virtually complete. The indestructible frame is mated to the reinforced body, the safety systems are structurally integrated, the heavy-duty drivetrain is perfectly aligned, and the advanced electrical nervous system is actively communicating. The vehicle looks incredible sitting in the garage, a massive, imposing machine that clearly dominates any other toy on the market. But despite all of this mechanical and electrical perfection, the vehicle is not yet safe to drive. In fact, if you were to unplug the charger, put your child in the seat, and let them accelerate down the driveway right now, you would encounter a terrifying and potentially disastrous problem the very first time they took their foot off the gas pedal. Because this machine utilizes advanced electronic speed controllers and high-torque motors, it features a highly specific regenerative braking system that requires a mandatory, manual calibration sequence before its maiden voyage. If you ignore this next critical step, the vehicle will absolutely fail to stop. The vehicle will absolutely fail to stop. To understand why this mandatory calibration is so utterly essential, we have to look at the historical trends of how children's ride-on vehicles handled deceleration in the past. In a standard mass-market 12-volt toy, the gas pedal is nothing more than a crude mechanical on and off switch. When the child presses the plastic pedal down, a physical copper contact closes, sending raw voltage directly to the motors. When they lift their foot, that contact snaps back, instantly severing the power. But to stop the vehicle from freewheeling, that same switch simultaneously creates a dead short across the motor terminals. This violent short circuit locks the magnetic field of the motor, causing the vehicle to skid to an abrupt, neck-snapping halt. This archaic system strips plastic gears, ruins tires, and provides an incredibly jarring experience for the driver. Because our ultimate model utilizes a sophisticated electronic speed controller and massive dual 775 series motors, it abandons that destructive physical switch entirely in favor of an electronic potentiometer and programmable regenerative braking. But this advanced technology introduces a critical variable. Out of the box, the electronic speed controller does not inherently know the physical resting point of the accelerator pedal. Imagine if you are a parent like Robert, living in a neighborhood with heavily sloped driveways in suburban Colorado in the year 2026. Robert finishes building the vehicle, sets the child in the seat, and watches his son drive toward the street. As the child approaches the end of the driveway, he takes his foot off the gas pedal, fully expecting the vehicle to halt just like his older, cheaper toys did. But because Robert skipped the throttle calibration, the electronic speed controller still reads a resting voltage signal from the pedal assembly. It assumes the child is still asking for 2% throttle. Therefore, the regenerative braking sequence never engages. The heavy 150-pound machine simply coasts silently down the incline, gaining momentum as it rolls directly toward the active roadway. The potential outcomes of this scenario are terrifying and entirely preventable. To initiate the digital handshake between the pedal and the computer, we must enter the diagnostic mode on the liquid crystal display. With the vehicle powered off, you must press and hold the main ignition button, while simultaneously holding the physical headlight toggle switch on the center console. After 5 seconds, the dashboard will emit a sequence of 3 sharp tones, and the display will transition from its standard media interface to a raw diagnostic readout showing real-time voltage parameters. You will see a data line labeled throttle input voltage. Right now, it is likely fluctuating randomly. Your job is to slowly press the accelerator pedal perfectly flush to the floorboard and hold it there for 3 solid seconds. You will see the voltage readout climb and stabilize at its maximum value. This teaches the brain of the vehicle the absolute maximum physical limit of the throttle travel. Next, you abruptly slide your foot off the pedal, allowing the heavy return spring to snap it back to its resting position. The screen will register a new, much lower voltage number. You press the media play button once to lock this value in the memory bank. You have now successfully established the dead band. The electronic speed controller now definitively understands that when the pedal returns to this exact physical location, the driver is demanding zero forward momentum, and it must instantly initiate the regenerative braking algorithm. Instead of physically shorting the motors and destroying the sintered steel gears, the computer smoothly reverses the electrical polarity, using the immense magnetic drag of the copper windings to forcefully slow the chassis down. This process captures the kinetic energy of the rolling vehicle, converts it back into electricity, and feeds it directly into the lithium iron phosphate battery, slightly extending your drive time with every single stop. However, the engineering team understood that relying purely on magnetic resistance to stop a machine capable of carrying significant weight at 7 miles per hour is a massive liability, especially on steep gradients. If the child is driving down a severe hill, the gravitational pull can overpower the magnetic regenerative braking, leading to a dangerous runaway situation. This brings us to the most visually striking and mechanically necessary upgrade on this entire chassis. If you look closely through the spokes of the rear 14-inch rubber tires, you will see actual ventilated stainless steel brake rotors bolted directly to the wheel hubs, clamped by heavy-duty mechanical brake calipers. We are looking at a fully independent, foot-actuated disc brake system on a children's toy. But just like a real passenger car, a disc brake system is not fully effective the moment it rolls out of the factory. The brake pads are manufactured with a smooth, glazed surface, and the stainless steel rotors have microscopic machining imperfections. If your child tries to slam on the brake pedal during their very first high-speed run, the hard pads will simply slide across the smooth steel with virtually zero friction, resulting in a dangerously long stopping distance. We have to perform a procedure known as bedding the brakes. Let us look at a case study of a family navigating the steep, rolling hills of a park in San Francisco. To ensure absolute safety on those inclines, the parents must first take the vehicle to a flat, open expanse of pavement. Using the parental override transmitter we discussed earlier, you place the vehicle in its lowest speed setting. You drive the vehicle forward at a walking pace, and then firmly press the secondary mechanical brake pedal, located on the far left of the driver's footwell, to bring the chassis to a complete stop. You must repeat this low-speed start and stop process approximately 20 times. As you perform this repetitive cycle, the intense friction generates heat. This thermal cycling purposefully melts a microscopic layer of the abrasive brake pad material and aggressively embeds it directly into the pores of the stainless steel rotor. You are physically transferring the friction compound onto the spinning disc. After completing this cycle, you will visibly notice that the shiny silver rotors have taken on a dull, slightly bluish-gray hue. This is the visual confirmation that the transfer layer has been successfully established. The mechanical bite of the calipers is now exponentially stronger, capable of locking up the heavy rear rubber tires and bringing the 150-pound machine to a dead stop on a steep downhill grade, providing a critical mechanical fail-safe if the electronic systems ever become overwhelmed. The vehicle is now structurally indestructible. The lithium power plant is actively managed and protected from parasitic drain. The drivetrain is perfectly aligned. The safety harnesses are anchored to forged steel, and the dual braking systems are meticulously calibrated to handle emergency deceleration. You have successfully navigated the complexities of assembling a high-performance machine in the year 2026. The unboxing and assembly masterclass is entirely complete. But as you look at the parental remote control transmitter resting on the dashboard, you might notice a small rubberized plug covering a recessed data port on the side of the handle. Behind that plug lies a digital gateway to a hidden firmware menu that the manufacturer was legally obligated to restrict from the general public. There is a specific combination of inputs that disables the factory speed limiters, completely uncorking the raw voltage potential of the battery management system and transforming this heavy-duty toy into a machine that defies every historical trend in the industry. We are going to plug into that port, access the restricted developer menu, and show you exactly what happens when you remove all the digital guardrails. We are going to plug into that port, access the restricted developer menu, and show you exactly what happens when you remove all the digital guardrails. By peeling back the small weather-resistant rubber seal on the left side of the transmitter, we expose a standard data terminal. This is not for charging the remote battery. This port establishes a direct, two-way serial communication link between a diagnostic computer and the primary electronic speed controller mounted on the vehicle chassis. Using a specialized data cable, we bridge the transmitter to a laptop. The software we are booting up is an engineering interface, typically strictly reserved for factory calibration and quality assurance testing. What we are looking at on the screen is a raw hexadecimal readout of the vehicle firmware. This is an educational exploration of the potential outcomes when you bypass consumer safety limitations, and it perfectly illustrates the hidden capabilities engineered into this 24-volt architecture. Historical trends in the consumer electronics and ride-on toy markets show a massive disconnect between hardware capability and software allowance. To comply with strict international toy safety regulations, manufacturers artificially bottleneck the performance of their electrical components. The massive lithium iron phosphate battery and the dual 775 series motors we just assembled are mechanically capable of drawing and processing over 40 amps of continuous current. However, the factory firmware hardcodes a strict 15 amp ceiling into the electronic speed controller. This digital governor is exactly why the top speed is permanently locked at 7 miles per hour. The software literally starves the motors of the voltage they were designed to handle. But by navigating to the parameter configuration tab within this developer menu, we can rewrite that logic. We locate the specific hexadecimal string that controls the pulse width modulation duty cycle. Pulse width modulation is how the electronic speed controller regulates power. Instead of sending a constant stream of electricity, it pulses the power on and off thousands of times per second. At maximum factory throttle, the duty cycle is artificially capped at roughly 60%. This means the motors are technically off for 40% of the time you are pressing the pedal to the floor. We are selecting that value and manually increasing the maximum duty cycle to a full 100%. We are also locating the ramp-up delay, which is the soft start feature that prevents sudden jerking, and we are reducing that delay from 2 full seconds down to 0.2 seconds. We are effectively commanding the battery management system to dump the entire 24 volts and uninhibited amperage directly into the copper windings of the motors the absolute microsecond the throttle reaches maximum depression. Imagine if you are a parent like James, living on a massive rural property in upstate New York in the year 2026. James has spent the entire weekend assembling this machine and understands the mechanical limits of the steel frame and the pneumatic rubber tires. He flashes this modified firmware to the vehicle, unplugs the data cable, and takes the chassis out to a wide-open, perfectly flat expanse of packed dirt. The vehicle is completely empty, operating exclusively via the remote control transmitter. James pulls the throttle trigger all the way back. The potential outcomes of unlocking the pulse width modulation instantly materialize in a violent display of physics. Because the soft start delay is gone, the massive instant torque generated by the unrestricted motors overwhelms the mechanical grip of the 14-inch rubber tires. The heavy all-terrain treads actually break traction, spinning frantically and kicking a massive roost of dust and gravel into the air before finally biting into the earth and launching the 150-pound machine forward. The sound profile of the vehicle completely changes. The mild, heavily suppressed electric hum is replaced by an aggressive, high-pitched whine reminiscent of a professional remote control race car. As the vehicle tears across the field, you can physically see the suspension system working at an entirely new capacity. At 7 miles per hour, the coilover shocks barely registered minor bumps. But as the unlocked vehicle aggressively accelerates past 10-12 and approaches a staggering 15 miles per hour, the kinetic energy multiplies exponentially. When the front tires strike a deep rut at 15 miles per hour, the independent steel suspension arms slam upward, compressing the heavy gauge springs to their absolute maximum limit, and the hydraulic dampeners work furiously to push the tires back down to the dirt. The chassis remains terrifyingly stable, proving that the tubular steel roll cage and the wide track width were not just cosmetic aesthetic choices. They were engineered precisely to handle this exact level of extreme dynamic stress. Case studies involving hobbyist modifications of mass-market electric toys usually end in catastrophic thermal failure. If you attempted to force a 100% duty cycle on a cheap, unibody plastic toy with standard 390 series motors, the internal copper windings would reach their melting point within 3 minutes. The plastic motor mounts would literally liquefy, and the gears would shatter. But as we bring this unlocked beast back to the garage after 20 minutes of sustained, high-speed driving, we aim a thermal imaging camera directly at the rear gearboxes. The aluminum heat sinks on the electronic speed controller are warm to the touch, and the internal cooling fans on the motors are spinning aggressively, pulling ambient air through the ventilation slots. However, the core temperature remains well within the safe operating margins of the sintered steel gears and the heavy-duty nylon housing. The lithium iron phosphate battery, protected by its advanced management system, shows zero signs of thermal runaway or voltage sag. The engineering holds up flawlessly. We have successfully stripped away the illusions of the toy industry. We have exposed the raw industrial-grade performance hidden beneath the plastic body shell, proving that this is not merely a ride-on car, but a scaled-down, legitimate recreational vehicle. You now possess a comprehensive understanding of every single bolt, wire, circuit, and line of code that makes this machine the absolute pinnacle of backyard engineering. We have witnessed the destructive torque, the unyielding steel chassis, and the massive speed potential when the digital shackles are removed. The unboxing, the deep-dive mechanical assembly, and the software calibration are definitively complete. But testing an empty chassis on a flat dirt field only scratches the surface of what this 24-volt architecture can actually conquer. What happens when we completely submerge the weather-sealed electronic speed controller in a creek crossing? What happens when we load 2 heavy passengers into the cabin, strap them into the 5-point harnesses, and point the nose of this machine directly up a steep, muddy 30-degree incline that would stall a traditional gas-powered all-terrain vehicle? The true test of durability is about to begin, and the structural integrity of that steel frame is about to face a challenge that it may not actually survive.